Welcome everybody to my paper presentation, which is about FRASHER, which is a framework for automated evaluation of similarity hashing. My name is Göbel. I am a PhD student at the University of Bundeswehr, Munich, and I worked on this paper together with master student Uhlig and with our supervisors Harald, Baier and Breitinger. So before I introduce you to the concept of fuzzy hashes, let me remind you about cryptographic hashes, which are a very central and important technique in information security, as it allows us to check the integrity of digital artifacts. The hash, as we can see in the figure, hash functions used here produce deterministic and collision-resistant hashes, meaning that there are no two different inputs that result in the same hash. So in this case, if we have two files that only differ in a few bytes and hash them, this would produce completely different hashes that are unique for each file. Fuzzy hashes, in contrast, however, are non-cryptographic hashes, meaning that they do not provide the properties of a cryptographic hash, like we just heard about, like collision resistance or pre-image resistance. Instead, they are used to determine a similarity, because if you have two files that only differ in a few bytes, as we can see here again, and produce fuzzy hashes, these fuzzy hashes are very similar in the parts where the original two files are similar. And thus they are a very concise representation of a digital artifact that simultaneously, in contrast to the cryptographic hashes, preserve all its sort of shared content with other files. So in other words, it keeps the similarity of different files. The actual similarity, as we can see in the middle, is expressed through a similarity value, or also called a similarity score, which is an indicator of the relation of the two files. Fuzzy hashes were originally intended to deal with spam. Over the years, however, we could observe that the creation of lots of fuzzy hashing algorithms. The ones we see here, like ssdeep, MSH, V2, sdhash, and so on, are only a few of them, which were released in the last 10 years. Actually, they work at least partially different. For example, they differ in the way they select the features, as we can see here. They differ in the way they generate a digest, or differ in the way they compare the digest. Or in other words, they measure the actual distance between two similar hashes. Fuzzy hashes are indeed a very powerful tool, because they allow us to assess the relation or similarity of various digital artifacts, as I said, and as we can see here. This kind of hashes are used in processes like spam detection, as I already said, but also for malware detection. So two prominent algorithms called ssdeep and TLSH are actually used in Google's VirusTotal. And also they are used for quite a bit of time in the digital forensics fieldwork. So the process of assessing the similarities through these fuzzy hashes, in other words, comparing multiple hashes against each other, is called approximate matching. However, approximate matching is not the definitive term. Over the years, we also heard of different terms like fuzzy hashing, like similarity digest comparison, or some of you might have heard of locality sensitive hashing. However, even if the process may vary in detail, all of them roughly describe the same process. And like I said before, there have been released lots of different algorithms. For example, some of them work based on text and others work based on raw bytes. So our framework to evaluate fuzzy hashes, which is called FRASHER, has a direct predecessor, which is called FRASH. And FRASH was developed in 2013 and published by Breitinger et al. So at that time, not so many approximate matching algorithms were known. And this is why the framework only supports two fuzzy hashing algorithms, namely ssdeep and sdhash. And also it only supports 5 test cases during release. So furthermore, the framework was written at Ruby at that time, what kind of means a problem in some cases. And in comparison to FRASH, our extension is called FRASHER. and is now written in Python, in actual current Python version 3, and runs in current operating system with current libraries. FRASHER includes more fuzzy hashing algorithms, 7 in the meantime, and at the time of writing, we supported 6, which is why the evaluation steps in the paper are done with 6 algorithms. And in the meantime, we also added nil-simsa. So furthermore, there are 9 test cases, which we can see in the figure here so far. All of them I will explain in the next slides. During the design phase of the framework, one important thing for us to mention was, or to pay attention to, was to kind of have a modular architecture so that the user can extend the framework, for example, by the means of future approximate matching algorithms, or by further test cases, or further visualization aspects, and so on. And another major advantage over the original framework is that we now have a graphical representation of the results, so as we can see in form of graphs. Furthermore, all tests are repeatable and can be adapted. So for example, by configuring a test to use different test data, or perform the same test in any number of test runs. And here's a short overview of the workflow of how FRASHER actually works. So in the first step, FRASHER takes a so-called playbook in a JSON format as an input. In this playbook, we can configure or specify all kinds of variables, like which algorithms we want to use, or which tests we want to run, or how big or small the test files should be, or the actual path of the test files, and so on. And in the second step, the test cases take the configuration in the playbook as an input, and according to the given specification, they generate certain test files, which are also saved for later use at the specified location. So as I said, we can repeat the same test multiple times. And in the third step, the test cases themselves then sort of apply the fuzzy hashing algorithms onto the freshly generated files. That is, all files are hashed, the similarity scores are taken and passed onto the evaluation module. And then the evaluation module calculates all kinds of metrics like the accuracy or the false positive rates, etc. And for each test run, these test results are then appended to the playbook, or back to the playbook. And if the user chooses so, the results also get graphically visualized, as I said, like in form of graphs. So now let me introduce you to the first test family of test cases that our framework FRASHER provides. Those are the efficiency tests, which are very important, you can imagine. So there's a generation, comparison, and compression efficiency test. And in this test, all algorithms are evaluated with the T5 corpus, which is mainly widely used in digital forensic research, but can also be switched with another corpus. In the case of generation efficiency, we pass the whole corpus to the fuzzy hashing algorithms, and we asked ourselves the question, how fast can the algorithm generate a hash of all files within it? In the case of the comparison efficiency test, we hand over the T5 corpus and ask how fast can the algorithm compare given files within the corpus. And so there's two different comparison efficiency tests. One is the all versus all test, where the algorithm has to compare every file of the corpus against all other files. And the second test is the one versus all test, where we take a single file and the fuzzy hashing algorithm has to compare this single file against all others. And third, we have the compression efficiency test, where we hand over the T5 corpus and we sort of test how effectively the algorithm can compress the whole corpus into a hash representation. So for fair comparison, we repeated this test 10 times and averaged all results. And actually, the number of test runs for each test we want to do with FRASHER can be configured in the playbook as a side note here. With regards to the digest generation results, the algorithms are all very close in regards to how long it takes them to create the digest of the whole corpus. However, it has to be mentioned that fbhash is pretty slow here. During the all versus all test, meaning that we compare each file within the T5 corpus with all other files, we found that fbhash is actually not able to do an all versus all comparison, so it doesn't offer a switch to do so. TLSH here is very efficient. After that, MRSH-CF and ssdeep are in a second place, and MRSH-v2 and sdhash are in a third place. In the one versus all comparison test, TLSH and ssdeep showed that they are built like for scale and are very, very efficient, so they can solve this task very fast. And FPHash is very slow here and thus actually not being usable in a real-world scenario. And the measurements of the remaining algorithms are all very close together. So looking at the compression efficiency results, at the one hand, we have TLSH and ssdeep, which are both two well-maintained algorithms who are capable of compressing or representing a file through a very small digest. So we can say they are kind of designed for use in scale. And can be used to search through quite large amounts of data. In the middle, we have the two multi-resolution hashing algorithms and sdhash, which all create digests that are very or fairly similar size. And then at the other end of the spectrum, we have FPHash that does not compress at all. Instead, it actually takes the 1.9 gigabyte large T5 corpus as an input and generates almost 10 times bigger output. So now let me introduce to the next family of tests that we performed, the so-called sensitivity and robustness tests. They are intended to evaluate the algorithms with regards to how well do they perform in a scenario where there is duplicate content or where two files have only a very small shared fragment. So we can ask the question, how small can the fragment get for the algorithm to still find it? These tests were performed with random generated data in order to prevent any distortion, as we can see here, like any distortion of the similarity score through unintended similarities that might occur in real-world files. Actually, we are aware that this is an idealized setting, but the actual behavior that the algorithms show with this kind of random data, let us predict how the algorithms would deal with a similar setting using real-world files. So the first test of the sensitivity and robustness test is called single common block test. For this test, we randomly generate two files which have the same length. As I said, in order to make sure that they don't have any shared content, like just right from the beginning. And then we insert a common fragment to both files. The common fragment takes up about 50% of the two files at the beginning, and then is inserted or these inserted common fragments are reduced step by step. So the similarities are made smaller and smaller. And after each round, the similarity score is taken and the resulting hashes are compared. So this procedure is then repeated until there's no more measurable similarity. And what we want to find out is what is the smallest size of the common fragment in two files that are otherwise completely different, but that the fuzzy hashing algorithm can still discover. So now looking at the results for the first time, we can also see the visualization component. So how the results coming out of the framework of FRASHER. On the x-axis here, we have the fragment size, and on the y-axis, we can see the similarity score. So the similarity score of the different tested algorithms, each shown in another color, are shown as graphs. And as the common fragment in this test gets smaller and smaller, it makes sense that the individual graphs go lower and lower as well. So the blue and green and brown line here start at a similarity score of approximately 50%, which is quite a good representation of the size of the common fragment within these two files at the beginning. And especially the parse or the similarity score of FPHash and MRSHCF match quite good to the actual inserted fragment size. The orange graph represents TLSH and shows that the similarity scores that it returns are always somehow a bit too high, as the actual shared fragment is much smaller. So it tends to misrepresent the actual commonality in those files. On the other side, we have the algorithms like MSH-V2 or sdhash, which also tend to misrepresent the actual commonality. As for both algorithms, the similarity score is always a bit too low. ssdeep sort of needs at least 30% of commonality to match anything at all, which we can see here. And so in this test, we can say MRSH, CF, and FPHash represent the size of the common fragment very accurately. And furthermore, besides the test files with a size of 2048 kilobyte, we also performed the same test with other file sizes, like smaller or bigger files. And the resulting graphs looked very similar, which is why we only put the one figure here. So this test here is intended to evaluate the alignment robustness of fuzzy hashing algorithms. So we have two instances of the same file, A and A prime, while A prime is increased in each round through either adding bytes, random bytes at the beginning or at the end of the copy. And the similarity score is measured after each round as one of those files grows bigger. With this test, so we can simulate, for example, the behavior typically seen in log files that normally grow continuously and especially often grow rapidly in the end. And so with this test, we want to see how well the algorithms perform in such a scenario where the comparison is between two files of varying sizes. Looking at the results, we performed this test as well in multiple test runs with files of different sizes, and performed it both for adding bytes at the end and the beginning. And it is interesting what can we see in the purple line, that sdhash shows different behavior depending on whether we put the random bytes at the beginning or the end. So we can say that it is not very alignment robust. And all other algorithms sort of show similar curve, which does not depend on whether content was appended or prepended. However, FP-hash similarity score, again, is always a bit too high and thus misrepresent the relation. The similarity score of both MRSH algorithms represent the proportions of the shared content in the two files very well, as one of them grows bigger. And ssdeep and TLSH have somehow a point where the growing file becomes too big compared to the small one. Or in other words, the relation becomes too insignificant for the algorithm to represent it. And then just, yeah, go quite or kind to zero. Now with the fragment detection test, we want to see what happens when we minimize the same file A prime and compare it with its original copy A that has not been minimized. So the file A prime always represents the smaller fragment of A here. And looking at the results in the brown graph, we see FP-hash, which similarity score again misrepresents the commonality with a consistently too high similarity score. MRSHCF shown in green represents file A prime, so the copy that is getting smaller and smaller very accurately, we could say. TLSH shown in orange shows a similar behavior to the alignment robustness test in terms of that it stops at some point to reflect any relation between those files. And the same also applies for ssdeep, which in this case shows a very consistent behavior, that there are relations that are just too small for ssdeep to reflect. So we can say it struggles as soon as more than 60% of the original file is removed. And the MRSH v2 represented in red, a similarity score always represents the similarity score of the smaller file in this case, which in this case leads to consistent values that are close to 100 and just breaks off in the end once the cutoff is like bigger than 90%. Then the similarity score approaches zero very rapidly. So now let me introduce to another family of test cases, so-called adversarial resilience test cases. With these test cases, we want to examine the behavior of the algorithms in the presence of active impediment during the digest generation and the digest comparison phases. So we want to evaluate how easy it would be for an attacker to sort of bypass the digest generation or comparison of fuzzy hashing algorithms. For example, we evaluated if it is possible to create a file that has very low variances, therefore not hashable by the algorithms. Or we also want to find out what is the smallest input that the fuzzy hashing algorithm still need to process, or also how a repetition of similar content affects the digest comparison phase. So now for the low variance version, what we basically did is we created text files which always had the same length, but were made up of a small and small amount of ASCII characters. So this way we could sort of see, can fuzzy hashing or a fuzzy hashing algorithm deal with a text file that has only just like a few unique characters left. And for the results, so for the digest generation impediment research question is clear. Can we create an input that is either too small or has too low variance so that the digest cannot be correctly generated by the fuzzy hashing algorithms? And for the results, looking at the results, we can see that ssdeep and MRSHCF can hash and match any input starting from 10 byte size, which is the minimum size in this test. And even if it has very low variance, TLSH, in contrast, needs a minimum of 50 bytes and a variance of at least 2 unique characters in any input. MRSH v2, you can say if you give it files that are smaller than 2,900 bytes, they must at least contain more than 100 characters, otherwise they cannot be reliably hashed. So it would be feasible here to get a file that has like 2,500 bytes and its content is made of less than 100 characters, and it could make its way through a filter that MRSH v2 is part of. sdhash revealed itself to require a minimum of input size of 512 bytes, and there need to be at least a variation of 8 characters up to a point where the file is at least 750 bytes long. And for fphash, it could be said that it requires a variance of at least 3 characters in any input file in order to be able to hash and match it. For the digest comparison impediment, we wanted to evaluate if an attacker that would concatenate a file multiple times, what we can see here, with itself, if it could pass content through any filter that is made up of fuzzy hashing algorithms. So what we can see, the same file is attached multiple times as an input here. And what we did is basically we randomly generated 5,000 bytes and we concatenated them multiple times with itself, what is mentioned as a multiplication factor here. And then we compared a single instance of the file with its multiples after each test run. And what we can see is that ssdeep and TLSH are not able to deal with files that are highly repetitive. So, or in other words, with files that consist of multiple times of themselves. And also the similarity score of MRSH-CF is kind of inconsistent here, which shows that it also can be lowered through deliberate duplication. All other algorithms can deal with this issue quite well. So the last test case I want to show you is the so-called finding the needle test case. This test is performed with real file types in contrast to the random generated bytes we used in the other test. So we used docx, PDF, JPEG files. Actually, we extended the T5 corpus with compressed file formats such as PPTX, XLSX, and so on. And what we wanted to do here is we want to find out how performant an algorithm is when it has to find a single file among many others. So this test literally matches to a test like finding the needle in the haystack. Therefore, we took multiple files of various file types and we manipulated them. For example, in terms of we compressed them, we cut them, we made them larger, we made them smaller, we mixed them with content of other files and so on. And in this way, we created 10 different needles for every file type. And by using approximate matching, the algorithms then had to find the original file within the test corpus. So this basically reflects a search for the non-manipulated version of the needle. And the file with the highest similarity score is considered as a success here. So if the file with the highest similarity score was the original, then we would consider this as a true positive. So the key takeaways from the finding in the needle tests are that ssdeep and TLSH are only usable up to a certain extent. The MRSH v2 and MRSH CF are the ones that perform best here. They were able to find the original to a file that has been manipulated very effectively. FPH, in contrast to in comparison, is too slow to be used at scale. The tests we performed took the algorithms altogether like maybe 45 minutes, and FPH would have taken quite a few days, in fact. sdhash is very ineffective for most file types, could be said, so its visibility is very poor in this test case. And what's interesting is that MRSH hashing can deal quite good with compression. So one of the needles, namely the needle 9 here, basically was a compressed gzip file with the highest compression setting, and MRSH algorithms produce a rather large hash. So I would say they are therefore able to still find traces in the compressed file. And further details, look in the paper, please. So our conclusion is that FRASHER greatly simplifies the evaluation of byte-wise approximate matching, both for using randomly generated data as well as real-world data, and FRASHER also reveals valuable insights into the capabilities of the approximate matching algorithms. We saw that MRSH hashing is just like, especially in the last scenario of the finding the needle test case, that these kind of algorithms are preferable in digital forensics fieldwork, since they detect pretty much and they consistently produce very good outputs that are very accurate. However, they produce quite a large hash, so it could be an issue in kind of production or automation. TLSH and ssdeep are very much purpose-built algorithms. As I said, they are very good maintained, and they are used in VirusTotal, for example. Both allow for better integration at scale. They have a very effective compression and they are very fast. However, its users need to be aware of the minimum of shared content of, like, for example, ssdeep needs at least to find any successful relation between two files. FPHash does not compress and therefore is very slow. Its authors are aware of this issue, and as we have seen as of last month, there has been a newer version called FPHash-E released, and it was released in the Digital Investigation Journal. And as soon as the source code would be available, we can evaluate this further algorithms as well with FRASHER. sdhash could be said is outperformed in most test cases by newer algorithms, and can't be recommended. So FRASHER sort of revealed a paradigm that exists in the world of fuzzy hashes, we could say so. That is that you can either have scalability or very well detection capabilities. It is always a question of the hash compression. The better it is, the better the algorithms are usable in scale. So TLSH, ssdeep, as I said, both produce very concise representation of digital artifacts, therefore are preferable to be used at scale, but therefore partially suffer on detection capabilities. Whilst multi-resolution hashing algorithms, on the other hand, have better detection capabilities. However, the hashes they produce are rather big. So therefore, if you think about a solution at scale, we would recommend using TLSH and ssdeep, and vice versa. So for the future research, we want to extend FRASHER, like including or integrating more fuzzy hashing algorithms, and also like for more test cases, especially more adversarial resilience test cases. And another research we are looking into right now is deep learning assisted approximate matching. So fuzzy hashes in this case are combined together with machine learning or used together to find commonalities, or even better smaller commonalities in large amounts of data. So basically we take fuzzy hashes and we use them like with transformers or with other models that are used in natural language processing. And this would enable us to find smaller commonality. And FRASHER in this regard can already be used to reveal this sort of threats to validity, because we have to be aware of any sort of flaws in fuzzy hashing algorithms if you're going to like take these hashes and give them as an input to machine learning models. We're currently seeing a deep learning assisted approximate matching already being used in the real world, like shown here by the Microsoft Defender team, and also in current research. And for the bibliography, here are some slides. And with this, I want to end my talk and thank you for your attention. And here's the link to the publicly available GitHub repository of FRASHER and some email addresses you can use to contact us afterwards if you have any question about it. So now I would be happy to answer your questions.